Alright, so in this video we're actually going to get into it now by talking about solids of revolution and how we can apply what we learned in the last video to create something called the slicing method. Our objective here is to introduce the concept of solids of revolution and to introduce the slicing method correspondingly. If you hear random baby noises in the background, I'm so sorry. But it shouldn't be too loud, I hope. Sound off in the comments if that's not the case. In any case, I'll try to be louder than all the ambient noise. So what we are talking about here, solids of revolution, fundamentally, we're talking about solids, right? But the way that they're generated is by taking a curve, just a nice finite curve. And here I have two examples. I have one where we're going to rotate about the x-axis. So rotate about the x-axis. And another one where we're going to rotate about the y-axis. So regardless of where we're rotating, the idea is the same. That we imagine a solid being traced out by taking this curve and sweeping it out a full 360 degrees, or 2 pi, about this axis. So what that might look like is you take this point on the curve and you rotate it about it, and then you would take what, if you could think about it, the next one over and also rotate it. And piecemeal, you'd be creating bit by bit the solid. So right there, if you could imagine that that's got any volume to it, right? So when you are completely finished rotating the entire curve, though, you will get this solid, okay? So you can imagine that everything on the inside, in between, we're just taking this area. So this, let's see, some infinitesimal rectangular area, and we're sweeping it out and creating a disk. Right, so we're taking this we're taking this rectangle and sweeping out a nice disk like that. And if we add all those up together, that makes up our solid of revolution. Similarly, if we're looking at rotation about the y-axis, then we rotate about the y-axis counterclockwise in a similar fashion. Okay, and each point on that curve gets swept out. Sorry, that doesn't look right. That's better. Okay. And makes the corresponding solid. So in the first one, it looks kind of like a solid top, and the first one is kind of like a vase. So you'll see that in the second example, the difference, aside from the fact that it's being rotated about the y-axis, is that we're starting from not a point, but so the end caps are full circles, but everything inside is solid. It's filled out completely. And similarly, then we can imagine that we have some infinitesimal rectangle, but now it's horizontal. And then that is being swept out and made into a disk on its side. You'll have to excuse my artistry, but imagine that that is a disk. All right, so let's get into it. How do we actually calculate the volume of such a solid? we're going to talk about what's called the slicing method. It is colloquially also known as the disc or washer method. But that is, we're just going to call it the slicing method because it's more general. And it'll apply to a variety of cases that we'll see have a little bit of interesting pieces to it. So for the sake of illustration, I'm going to again draw a solid of revolution. We're going to rotate about the x-axis. And so this region that I'm going to bound so it's the solid is created by rotating it about the x-axis. Oh, it's a little off, I guess. There we go, roughly. And so imagine then that we have this infinitely thin rectangle. Okay, so this infinitely thin rectangle, which, if you remember, is the same setup as trying to calculate the area under the curve, or between two curves. But here, then, our infinitesimal rectangle has an area of f of x times delta x. And we're using this if we assume that y equals f of x. So that's the curve equation or function that determines the curve. So we know that that infinitesimal rectangle, right, that is the width of that rectangle. And when it sweeps out a disk, then we can imagine a very, very thin cylinder. Okay, that very thin cylinder, then, if we want to think about, so the key insight here we're using infinitesimally thin cylinders. Remember that such a volume would look like pi r squared h, where here r squared is actually the height of that, or the radius, which is f of x. So r is f of x. And h, that's the height of the cylinder, or the width of this coin shape, which is delta x. In other words, it becomes pi f of x squared dx. And here I'm using delta x and dx interchangeably, just because in the limit it's going to end up being the same. So all that is telling us is that the volume of a solid of revolution, if we want to find it using the slicing method, is the integral from a to b, where a to b are the endpoints for x. So x ranges between a and b. And that's going to be pi times f of x squared dx. And that formula, fundamentally, is how we're going to figure out the volume of such a solid of revolution. It's going to vary slightly later when we extend revolution to an arbitrary axis, okay? And in fact, we're going to see that pretty soon, okay? All right, so let's just do a basic example here. So example. we're going to find the volume of the solid of revolution generated by the region. Generated by sweeping out the region. Bounded by y equals square root of x plus 1. Sorry, x minus 1. Can't read my own notes apparently. For x between 1 and 5 about the x-axis. So to give you an idea of what we're talking about here, let's graph it. Desmos it if you want to. And our curve here looks like that. Okay, so here's 1, here's 5, 2, 1, -2. So you will imagine that the solid of revolution should look something like this. And we're saying, what is the volume of that solid? And so again, let's think about our infinitesimal piece here. So it's our disk that we're generating from this, sweeping out this rectangle, okay? It's really gonna be a cylinder then, right? So our left endpoint is 1, our right endpoint is y, and our f of x here is square root of x minus 1. So the infinitesimal slice is going to be pi square root of x minus 1 squared dx, which simplifies to pi x minus 1 dx. And so, if we want to find the volume, we just need to integrate from 1 to 5 of this, pi x minus 1 dx. Which shouldn't be bad, because this, all we need to do here is, this is a polynomial, so we'll factor out a pi, integral from 1 to 5 of x minus 1 dx, which is pi x squared over 2 minus x from 1 to 5. And then if we use our good old FTC2, we'll get 25 over 2 minus 5 in the first set of parentheses. And in the second set of parentheses, we're going to have 1/2 minus 1. All right. And then just clean that up. So that should be pi times 15 over 2 plus pi times 1/2. And that will be 16/2 pi, which is the same as 8 pi. All right, so what this is saying is that the volume of this solid right here, remember, it is solid, literally, like all the way through, right? You think of it as a wheel of cheese, but you've bored out some of it. Not bored out, like you've shaved off some of it, right? Then this is our area, 8 pi units, sorry, volume, 8 pi units cubed. That's our answer. Okay. Now, this original method that we're presenting is often called the disk method because the infinitesimal slice that we're taking out here is a disk. But sometimes it may not work out that way. And so let me just illustrate then what happens when we have what we call the go again. Okay, where we left off. Yes, we were talking about washers. No, I just got done talking about washers. Damn it, I'm gonna have to edit this out. Okay, so let's talk about the washer method. What this means is, what we're actually looking at here is, instead of looking at the area underneath a curve, we are going to be looking at the area between two curves. And to no surprise then, that means, actually, yeah, let's go ahead and use this. What we're looking at is sweeping out an area between two curves. And what that means is then our solid then is going to have a gap in between. And it'll be hard to see at first, just because when we're rotating it, right, it just looks like we're doing a revolution, a regular solid of revolution. But really, in fact, oh boy, hope this is clear enough. It's got this nice gap in between. And so if you think about what's actually happening here, our infinitesimally thin rectangle then is not actually a disk now. It's shaped like a washer, and washer in the sense of like hardware tools, right? Like when you're building something, right? You got this nice washer like this, something like that. Boy, that's terrible. Sorry. But the idea is actually the same. It's not too bad. So the infinitesimally thin slice now is going to be the area of that ring or annulus. So, or sorry, the volume. I keep doing that. So what we're doing here is we're taking an annulus with major radius. If this is f of x, and this is the lower curve is g of x, then we've got major radius f of x and minor radius g of x. And the area formula for that would be something like dA equals pi r squared minus little r squared. So major radius is capital R squared, and minor radius is little r squared. That will end up being something like pi f of x squared minus g of x squared, like that. And of course, because the annulus, we can turn that into a nice little pineapple slice, right? So give that a little bit of thickness. Sorry, this is getting really convoluted. But if you give it a little bit of thickness, then dV becomes that whole thing times dx, because the thickness of that piece, the infinitesimally thin slice, is dx. All right, all that is to say that then under the washer method, the volume of such a solid is the integral from a to b. X ranges from a to b. Here's a, here's b, of pi times f of x squared minus g of x squared dx. Not too bad. Not too bad. Okay, let's see an example with this. Just a basic example of using the washer method. This is still the slicing method, technically. It's like a subset of it, okay? Except in this case, the slice has a gap in the middle, right? So we're going to find the volume of the solid generated by rotating the region. So our region is bounded by y equals x, y equals x cubed, and the first quadrant. And then the axis that we're rotating about is the x-axis. So the x-axis is still what we're rotating this about. Okay, so let's draw it real quick. Okay, so I've got x and x cubed. It looks something like that. It's not exactly right, but just take my word for it. Here's one, here's one. And the top is y equals x. The bottom is y equals x cubed. And when you go and rotate that, it's going to leave this nice hollowed out space in between here. Kind of looks like a trumpet a little bit. Do you see that? Except there's not really a hole in it. It kind of starts from a point and then it opens up like a flower almost. Okay? So then our annulus here, with our infinitely thin width dx, looks something like this. Okay? So our dv, right, the thing that the infinitesimally thin slice is pi times f of x being the upper curve, okay, x squared minus the lower curve squared, and then times dx. So our integral then is the integral from 0 to 1. Those are the limits of integration. We know this because that's actually what the region between x and x cubed looks like. It is bounded between 0 and 1 of this next to the 6th dx. And when we integrate that, then it'll be the full. We'll just finish that up right here. So that's going to be pi times x cubed over 3 minus x to the 7th over 7 from 0 to 1. Now plug in 0 and that's not going to do anything. So let's just be smart about this. We're only going to need to plug in 1. That's going to be pi of 1/3 minus 1/7. And do a little bit of fraction arithmetic. And you get 4 pi over 21. And that is the answer. That's your volume. Okay, so not too bad. In the next video, we're going to really take this slicing method and knock it into gear. So we're going to get some real interesting things now if we apply it to rotation about the